Uh, I feel it's a privilege and honor that I have been given a session in this important conference, and I'm very thankful to the whole conference management. I'm going to talk about today about how AU decoration of perovskite BIFE O3 nanostructure can enhance piezoplasmon phototronics. I'm working in King Saud University. Last 15 years, I'm here as a professor. And the people who are interested in the work, they can go through my Google Scholar link and other links, and they can see where we can collaborate, where we can have the scientific discussions. And if somebody needs any kind of assistance regarding measurements, we have a lot of facilities here. And I'm the in charge of clean room technology here. And before I'm going to start, let me discuss what is a plasmon. When we discuss about a plasmon, it seems as if as an analog of a density wave in an electronic gas. It is just if we put an electric field over a metallic system where we have the separation of the charges positive and negative in one direction, positive in one direction and negative in another direction. And as if it passes as a wave through an electronic gas. And if we move this field away, what we will have, we have the recombination of these positive and negative charges. And here it is where we work as a, we call it as a Julian model also. And this phenomena is about in metallic structures where we
Sir,
have
sorry
free
to interrupt
electronic gas.
you, Dr. Khalid. Your
Yes,
slides are not moving. You have to just click the slide on which you want to show because it got stuck on the first slide, sir.
is it now okay?
No, it's still on first slide. Yeah, no, what is plasmon? Yeah.
Uh, is it visible fully?
Yeah, it is visible. Sir, you have to just click the slide which you want to show.
Okay, so that means it's not, the full screen is not working here.
Yeah.
Okay, so this slide is completely visible.
Yes, sir. I think this slide number is second.
Yes.
Yeah. Carry on, sir.
Okay. So we are talking about an electronic gas in a metallic structure where if we apply an electric field, then we have the separation of the charges like a dielectric system where positive charges and negative charges get separated to some distance. And since this model is working in electronic gas system, we call it also a Julian model. And where we use it. So since I believe that all of you are working in nanostructural materials as we have a quantized confinement in nanostructures, especially when it is working in thin films and nanorods and nanoparticle structures. These are actually the boundary conditions of plasmons. And in a plasmon, actually, it's a metal structure. As I mentioned, it was long before Gustav Moy, who actually calculated 100 years ago how this resonance in metallic structures is happening. And this resonance energy is actually, and its color is dependent upon the size of the material. And the color also changes as the size of the material is changing, especially in semiconductors. And we have witnessed a different color systems in, for example, in luminescent materials like zinc oxide, titanium oxide, and other materials. And some of the pictures I may show you in the coming slides. So what is actually is happening in these confinement of single electrons, it shows a kind of a higher resonance energy, which we call as a blue shifter. In a plasmon resonance, we have a particular frequency in an electronic gas where we see the oscillation of an electron, and these frequencies are proportional to the electronic density. That means as the resonance frequency increases, it shows as if that the force constant we have, F is directly proportional to force constant K. Here we have omega P. If we say it is a plasmon frequency, that is directly proportional to the number of electrons or the electron density in a system. So how we are going to witness such kind of phenomena? We have to perform such kind as, for example, an uh, electron energy loss spectroscopy, where one of the electron spectroscopy graphs I have presented here, where you can see different peaks are mentioned, and we have almost four peaks, and the major peak is observed at 10.3 electron volt, and as the progressive beam goes on, there is a from the peak 1 to peak 2, peak 3, there is a consequence electronic energy loss. This is a kind of the interaction of the photon with the material, where we have this loss of energy, the absorbed energy loss. Where we are using these plasmonics, mostly if you look into the data structure we have nowadays from uh, the conventional system which we have, this earthen net system, we can move from an Ethernet system, and we can use kind of a fiber optics, where data can be transferred very smartly, very quickly in the smartphones as well as in the computer systems. And that means the data which is usually moving from an electrical pulse system can be transferred with the speed of light. So the systems will be much more faster, as we may not imagine that how fast it could be if we are introducing this plasmonic metallic films or systems. Usually, the plasmonic metal films are more than 100 times thinner than the glass fibers. If we are talking about the fiber technology and the fiber systems, we have the network optics. The thinner the system is, the lighter the information technology will be, and the more faster it will lead to the data transfer. So this is one picture, as I was discussing about, that how this size changes or the light absorption is going to uh, present you the two different pictures. This is the plasmon of gold nanoparticle in glass, which reflects the green one but transmits the red one. So there is a possibility of certain light beams are being absorbed and certain are being transmitted and certain are being reflected, and accordingly you will have the different kind of pictures and different kind of views. In overall, in a for example, if we are talking about the ITO, indium titanium oxide material, uh, as the light we try to put on a material like ITO, the incident light, a certain part of it is getting transmitted and certain part is getting reflected. Now the reflectivity cutoff at plasma energy can be used for energy saving window coating, which transfer visible sunlight but reflect thermal radiation. That thermal radiation into the part of the system where it exists. So, for example, where we are using these kind of materials, we have already encountered many transparent front electrodes. For example, we are using it on the panel of the surface panel of the solar cells. We are using them on the LCD screens. And if you touch the top of the LCD screen, somewhere you will find it is little bit warm. I may not say it's a very hot, but it's warm. That means that the heat energy is reflected in the medium where you are sitting, and the part of the light is getting transferred. So here we will see at lambda p, if we may say it, where the two transmitter light is and the reflected parts, they cross each other, and it is almost that we see that we have to minimize or we have to miniaturize the system, where the transmission part and reflected part, at least they should be equal. However, we have to minimize the reflective part. The transmission, the reflective part should be more and transmission part should be less. That's where the plasmonic research goes on, because if all the light gets transmitted through the medium, then we are losing that energy. Similarly, if the amount of energy which is the amount of light which is incident on a surface, and that gets completely convert it into the heat energy, that also is an issue. So we need a reflection, we need that absorbs of the energy, so that this energy can be converted into the system, and we can have the threshold electron release, and accordingly we can have the different material perspectives as we design their applications. Here, what is how we are going to combine optoelectrons with plasma nucleus. That's where the conversion of the light individual phenomena is coming into the picture. Usually, when we are talking about the black plasmons, they have a longitudinal oscillation parallel to the propagation direction, while the photons, we know, they are transverse. That means they are perpendicular to the propagation. So this kind of situation is not matching. The one is moving into the longitudinal direction, and the photons are coming into the transverse mode. So we need to have somewhere the crossover. So surface plasmons are transverse, but they are mismatched to photons in their momentum. That's where we apply a kind of a grating. That is, it is possible to provide the necessary momentum by a grating pair, which transfers the wave vector, the k, which is equal to 2 pi over d, and d, it's a line spacing in the grating mechanism. This, as we, for example, we are in the Gulf, and we have a lot of sunny days. We don't have much of a cloudy weather here, if as compared to the India. So in a solar day, if we are talking about, and considering that an average, the total solar energy striking to the Earth, and at an average is 120,000 terawatt. So this is a huge amount of energy which can be used. As the progress in the last 20 years, we have seen that at least from a certain quarter of the price, which was earlier before 20 years, it has reduced much. Nowadays, yes, by the time as we are working in the progress of the solar cell manufacturing. And we have here different kinds of solar cell. We have perovskite, we have dye-synthesized solar cells, and other cells. Although we are still, a way behind, because whatever the conventional cells we try to manufacture in the labs, only 44% of that can be converted into electricity. That means there's a mismatch of the wavelengths, of what is incident on the surface. A lot of energy is getting wasted, because our materials, they absorb from the UV spectrum. If we consider it this visible spectrum, we may take it as a Weber visible light. We have violet is getting absorbed, or indigo is getting absorbed, or orange is getting absorbed, and certain parts are getting reflected. So we need a conventional system where whole of the visible spectrum gets absorbed, and none of the wavelengths gets reflected in such a way that it is as a waste, or it gets transmitted. And so that's where the researchers all across the world, they are trying to work on different types of solar cells. One way to improve the methods to minimize the amount of light reflected from the cell or transmitted through it, since the energy is lost, is what we can do. We can put some kind of a anti-reflecting coating, but again, there is a problem. It's not going to work fully. That then whole of the lights can be reflected. That's one issue. We don't know which part is getting absorbed, which is not getting transmitted, which is not getting reflected. While these coatings prevent reflection, they cannot stop light from being transmitted. So as I mentioned, that's one issue. So in some cases, almost half of the light passes straight through the material. So again, it's a waste. So choose a selection of the material, a proper material where whole of the visible spectrum gets absorbed, or choice of a material, then doping it with an appropriate dopant. That selection process is going last more than 20 years. Now, when we are talking about these materials, we have to find out two ways how to trap this light. So we, in for example, we as a manufacturing of these devices, what we try to do is we have two phenomena. One is called as light trapping through LSP, that is a local surface plasmon, and another is surface plasmon. So in the local surface LSP, we have to design certain geometry in the material, and that depends also on the composition. And we have to we have to provide certain kinds of wells or the surface trapping center, so that the energy gets trapped. Or we have to move like on the surface mount, that as the light is incident and it is reflected and it moves on the surface of the nanostructure. So basically it depends upon uh, uh, both the phenomena, and what is more pronounced or what is more better in the fashion of making an advanced material is surface plasmon at the moment. So like you can see how the surface plasmons are working as the incident light uh, on metal particles roughly on the scale of wavelength of light, which is almost equal of the wavelength of light. They excite the surface plasmon, which can then scatter light and couple it into the waveguide modes. And this way, we have more and more, surface plasma activity on the surface, and the energy can be more and more absorbed. So let me go in the as a nanostructure materials when we talk about how this propagation of the lights are going to help. Since we are designing these nanostructure materials, they are very, very small, and the thin films which we design are of nanoscale. That those nanoscale uh, particles, they are more uh, feasible to attract the light when their energy matches or the wavelengths matches. So long propagation length is to use very thin films if we have to take for a longer propagation. So in addition of that, nanoparticles show strong optical resonance because of their large free electrons density, and ordered arrays of nanoparts can possess even further enhancement of the field intensity, which will aid the plasmon coupling between two adjacent particles. So what we are looking here is to design a geometry of a material, which is also dependent on the composition of a material and the environment of the chemical environment which we are providing, so that the phenomena of plasmon enhancement is working. What we did in our case, I'm going to present certain experimental work which we have recently published, where we have choose to BFO, bismuth ferrite, iron oxide, or simply the bismuth ferrite, which is a perovskite family, and the band gap energy of the material is which is narrow, from 2.1 to 2.7 electron volt. It has a high excellent chemical stability, and its cost effective features are very interesting. So as we try to do plasmon effects, what actually we are preparing, we are manufacturing here photoelectrochemical cells. These cells are very important cells which help us in solar cell light. When it is being irradiated on these, then the charges get generated, which react with the water molecules, and they can help us in the splitting of the hydrogen and oxygen. One of the areas which we are nowadays dealing is not only the energy from the sunlight to be converted into the electricity so that our roads and the lights can be illuminated. We also need the fuel for our cars, fuel for our other machinery systems. So here is if hydrogen, which is thought to be one of the important constant, and it is freely available all because it is abundant in our environment, so we can utilize this hydrogen. And for that, we need some catalytic system, where hydrogen can be separated from the oxygen, and the oxygen is, if the abundance of oxygen is there, that's okay. But hydrogen, that can be converted into the fuel, and we can use it in our uh, cars, in our other systems, and that will be much cheaper than the hydrocarbons, which is right now pricing at $80, sometimes $120, especially in the countries, developing countries like India and other, Bangladesh and Pakistan. It's they who are very much struggling with the energy crisis. So as the population is very high, uh, so here we designed a BFO structure, and we tried to decorate with the iron, gold. So gold is a kind of a material which is, very interesting material, and is helping in plasmon activity. So Aksadi shows us that the as the bismuth oxide were decorated with the gold, uh, it did not show any impurity peak. That means it has completely taken the structure of this the system, uh, and the rhombohedral structure was verified. Uh, as said, that we have the different activity of these materials, especially the we are looking for water splitting through these electrochemical cells, and depends upon that what kind of doping you are doing. If it's N-type or P-type, accordingly the semiconductor can be photocathode or photo and anode. So after development of this material, this structure, which I'm not going to discuss in detail, that how we prepared the material, you can go through the reference of this paper, and find out this fabrication of the material. What we did, we simply tried to perform X-ray photospectroscopy, where we visualize the individual elements, where the bismuth has shown its peaks at 164 and 158 electron volt, and similarly the iron has shown its presence in its respective valence states, and so is we try to find out about gold. Is gold the present? And that's very much there by visualizing the two different peaks. But as you compare with the pristine sample and the decorated gold sample, you can see we have the different, evaluation of the emergence of the two different peaks, and broader sizes in the C graphs noted as a C. However, if you look into the some images of these, we have in the morphology, it's A is the pure BFO, while as B is the morphology of the decorated BFO. And similarly, you can see the different transmission electron microscope images. We have, decorated the BFO with the different concentrations of 5%, 10%, 20%. That's why here you can see the different images for different compositions. We tried to have for understanding the optoelectronic properties. We did the UV spectroscopy. In the UV measurements, you can see that we have the emergence of the SPR, surface plasmon effect peaks, which emerge somewhere around 630 nanometer. And compared to that, if you look into the photoluminescence part, we see that there is a quenching effect happening, and it clearly evidences that there is a formation of a Schottky barrier. It has enhanced the luminescence, uh, and we see that the pure BFO is at the highest level, while as the BFO with decorated with the gold nanoparticles is at the lowest. And that means by looking at this picture, we see that they two are completely opposite to each other. That as the doping of this gold decoration, it's not actually the doping. We have, on the surface we have coated the gold, and this decoration of this has enhanced the surface plasmon, that somewhere we have been very successful. By looking at how was the photo current density of how this generated, how much energy was generated, we illuminated this material with 1.5 GeM intensity of the light, and we performed the material in two different aspects. For example, in the pure BFO, we did the experiment in the dark mode, and we had this in the light mode. And similarly, in BFO, decorated with the gold, again with the dark and with the gold. Here, what we did, we in one aspect, since this material is a piezo phototronic effect is being visualized, we had a different kind of activity where sono chemical effect, we had to sonicate the material. So the sonication was done in the dark, and similarly, the sonication was done in the presence of the light for the both the categories. What we observed for the pure BFO, the illumination in presence of 1.5 G, we had the photocurrent density of 10.84. However, as you have decorated the BFO with the gold, the photocurrent density has gone double. It is 22.44 microampere per centimeter square. Then we went for the stability test also. We had, before going for the stability test, you see that we did a chronoamperometric cyclic measurement, which was done in the time frame of 20 seconds, and the applied voltage was used at 0.8 volt, and it was done in the on and off mode. And we see in this cyclic mode that at least we had this complete stable state where we witnessed the stability of pure BFO, and also for the gold decorated between 65 to 73%. Nyquist plots show us this, semicircles, and the half circle or the pure full circle. They resemble to certain aspects, and here we witness that the gold decorated part has lower impedance compared to the pure BFO, which is also one of the ways to identify how this material is good for solar cell applications. Looking at the degradation part, we since we used this material for hydrogen production, we also tried, is it possible that the water, nowadays we see that there are a lot of chemical, a kind of impurity, I may say, that's mixing with the water, and we wanted to remove these and tried with different types of dyes, and we used the methylene blue, we used the methyl orange, Congo red, and chlorophenol. These were the four different kinds of dyes, and we found that the methylene blue was with the almost of 98% removal was possible using this kind of material. However, we tried also with the methylene blue dye concentration at a periodical periods, how this process is happening. Since we manufacture these materials with different processes, so that is piezo catalysis and piezo photocatalysis and piezo photocatalysis, the combination of, as I mentioned to you, that we had this in the different modes. So looking at this picture, you can see that this piezo catalysis part, it shows us the efficiency of almost 22% when we had only the photocatalysis. When was the photocatalysis and piezo catalysis? When you give the sonication to the material, you make this material to vibrate vigorously. We had that as a piezo catalysis part. When we had only the direct sunlight illumination on this material, that's the photocatalysis part. When you had the both, that means that you are using the sonication of the material as well as the illumination of light. That's a combination of the two. We call it a piezo photocatalysis. So in the piezo photocatalysis, we saw that the efficiency percentage is higher compared to the pure photocatalysis part or pure piezocatalysis part. And the degradation efficiency, accordingly, we saw that the cycle of the first efficiency was very high. It was almost 99%, but it went down as the progress with the, we try to reuse this material for the third cycle. And the absorption period, as you look into the picture D, the illumination part was only for the 30 minutes. The whole of the process was carried out during that part. And next, we tried how much amount of hydrogen production is there. We saw that the piezo photocatalysis part is somewhere we had the more success compared to the pure photocatalysis or the piezo catalysis part. We had almost reached to the four, you can see into the, the picture B, where we had achieved almost around 3,800 micromoles production per hour. So that, I believe that it was a success because of the decoration of the gold in this material. However, we tried to change this material. We had the different category. We thought that, okay, it was with the gold. Can we repeat this phenomena with the gadolinium? And we saw that there is the efficiency factor is, different compared to the gold one. So here it's a similar, the mechanism, which I'm not going to discuss in detail, how this process was performed. However, as I mentioned, again, the gadolinium, when it was, doped, we had almost, the pure structure, especially certain peaks at 200 and 111, which we marked that there was a certain, impurity peaks because of the bismuth iron oxide, which is usually a very difficult part to achieve, and the presence of these dopant agents as well as these the main matrix elements were visualized through the XPS. What we did here, we performed the surface measurements using this morphological technique, the SEM and TEM, and we saw that they are almost spherical in shape. We had this absorption study also. We tried to change the pH level of the material. We had at a pH level of 10 and 4, you can see that the factor of absorbance at the time scale of 10. After that, as the time reaches to 10 seconds, then we had a kind of a saturation is there. Similarly, we had this UV visible spectrum and photoluminescence part. We saw that again the gold decorated. There we had the gadolinium, as well as we had the decoration of this bismuth doped with the gadolinium, and over that we had decorated the gold. We saw that the gold part, where it is more pronounced plasmon surface effects compared to the just only the gadolinium doping. When you see this versus with the pH level, we try to see how the pH level of this material is affecting on the performance of these and the absorption of the dyes. We had here a tetrasilene as a dye, and we saw that for the highest absorption was achieved for the pH level of 10. However, if you go to the again that part where we had the different aspects to see that which one is more better, is it photocatalysis or piezocatalysis or piezo photocatalysis? We had the similar phenomena that it is actually the piezo photocatalysis decorated with the gold compared to the just a simple doping. It is where we had the highest percentage. That is, although the gadolinium percentage you can see is 5% here, but the gold decoration is over that all the systems, whether it's 1%, 2%, 3%. We kept certain parts as simply gadolinium. We had prepared two different systems without the gold decoration and with the gold decoration. Then we had to repeat the experiments. So we saw overall that it is actually the gold is helping us to achieve the more and more surface plasmon effects. So these were the two, uh, reports I showed to you, where we had the gadolinium doping and the gold doping. We prepared the material through simple hydrothermal methods and chemical uh, uh, processes. However, we had a different aspect where we choose to have simply, a green effect. Is the green synthesis going to achieve something better compared to the earlier reports? Let me go to the, this is the SEM and TEM images of these. We had, again, the uh, absorbance, where we saw that the BFO with the gold is having higher absorptions compared to the BFO pure. And we had the similar phenomena to see the stability test for the time in the dark and light mode. We had the current density, which was achieved way beyond for the 0.8. You can see that it has gone to similarly to almost 22 microampere. Similarly, if you compare the pure one with the uh, uh, pristine sample, with the gold decorated, here you can see the efficiency was increased for the gold decorated system, which is almost the 6.8. You can say it's 7%. For the pristine sample, it was 5.7%. So, in all, what we saw that there is, in comparison to the chemical synthesis and the pure green synthesis part, we had a different achievement. That means the green synthesis is somewhere helping to achieve better efficiency of these materials, and surface plasmon effects were much more pronounced with the gold decoration. So that's what I had to present, and I look forward to listen to if there is any kind of suggestions or comments from the teams.